as I say, I was kind of planning to give you a work day, but we'll just switch things around a little bit. We're going to continue with what we talked about yesterday, linear systems. But today we're going to introduce technology. We're going to talk about some ways we can use technology to quickly and easily solve linear systems. And we'll even push it into some linear systems. We hinted at systems that really, we call them linear, but they represent maybe even plane systems, right? So systems that involve more than two variables that we're accustomed to. And then next week we'll go a little further and we'll look at how to solve some more complicated systems, linear quadratic systems. All right, so let's review what we did yesterday. So why don't you get out your notes and just see, let's everybody work through this one together. Go ahead and click them all the way closed, please, once you get logged in. Let's talk through this one. Take a second and kind of get yourself oriented, and then let's talk through how we might solve this based on yesterday's review. Okay, so what method are we probably going to want to use here? Elimination, right? This one's not really set up for substitution because there's no variable that's easy to isolate. We want to use elimination. This is a little bit tougher than some of the ones we looked at yesterday. So we want to identify what's the variable that we probably want to target for elimination. What do you think? X. How come X? Smaller numbers, right? We get to multiply by smaller numbers. So we got a couple options. What's one thing we could do? What could we multiply the top equation by? We'll use our notation that we developed yesterday. We could multiply by 5. Okay, if we distribute 5 through both sides, what are we going to get? Negative 30x minus 45y minus 720. Good. Everybody agree? Okay. All right, so we got the first one. So in order to eliminate x's, because you said x's is what we wanted to eliminate, what should we multiply the bottom equation through by? Negative 6. Okay. And that's going to give us what? 30x minus 60y and 330. Yeah, we started this one yesterday, didn't we? Okay, so when we add these up, then what happens? X is canceled, good. Negative 105y equals, okay, works out pretty nicely. What do you know? And what's that give us then? If I divide both sides by negative 105, everybody agree? All right, so we got y, we're halfway there, now what? Plug it in. And we'll just pick which one appears to be the easiest. It's not so critical, but we'll try to make our work a little bit easier. Bottom one looks a little bit easier, slightly smaller coefficients. So then that's going to give us what? Negative 5x plus 10 times 10 is my y value, right? Equals 55. So now what? Okay, so we're just going to simplify. Negative 5x plus 100 equals 55. Subtract 100, right? Last two steps in order to isolate x. Subtract 100 and divide by negative 5. All right, so negative 5x equals negative 45. So what do we get for x? So how do we want to represent our answer then? Okay, well, what do we call that? Ordered pair. Ordered pair. So we get the ordered pair, 9, 10. And, we talked about this a little bit yesterday, and this is all review for you guys, I know that. What's the significance of this ordered pair graphically? It's a solution, you're right, it's a solution. But it's a solution even without considering the graph. We know it's a solution because it satisfies our original equations. And that's how I could check it, right? I could plug in my solution into both equations to verify that it's a solution of both. We kind of talked about yesterday what that means in terms of a graph. I don't know if we actually made a graph. That's what we'll do today. But what's the significance of that ordered pair if we were to graph those lines? What do you think? It's where they cross, point of intersection, right? And so this brings us to the first and probably the easiest method of solving linear systems, right? At least small linear systems. If we get something like that, how could we use Desmos to solve this thing? Graph it, do it. Just pull up Desmos. And if you haven't already bookmarked Desmos, do that. So just, if you search on Desmos calculator, or Desmos graphing calculator, it's going to take you where we want to go. The nice thing about Desmos, and we can kind of work through this one together, the nice thing about Desmos is that you don't have to solve for y, right? We can just enter these equations. Whoops, what'd I do here? Oh my goodness, there it is. Is that the right one?
Yes.
Yeah. Okay. So we can just enter them the way they look. On a graphing calculator, you have to isolate the y, but in Desmos, we can just do this, right? Negative 2x minus 2y equals negative 20, and it gives us the graph. Piece of cake. Okay, and so what'd you get? Okay, everybody agree? That's simple. We're just looking for the intersection. There it is, right? Okay, try another one. Oops. Try this. I forgot I had this. Okay, so let's do a quick application. It's been a while since you've done these, but we need a little practice, right? So let's see if you're going to have to probably think about this a little bit. See that maybe you might have to scratch some things out on paper and pencil, but ultimately we can use Desmos to maybe get our solution. I'm going to give you a second to think about this and work on it. We'll come back and talk about it. So Teresa needs to rent a car at the airport. There are 2 car rental companies. Eagle Rent-A-Car charges a flat fee of $26.04 plus a 15-cent per mile, plus 15 cents per mile driven. Easy Rentals does not charge a flat fee, but charges 77 cents per mile driven. So first of all, and we're going to ask some questions about these 2 companies. We want to know after how many miles will both companies have charged the same amount. Okay, we call that the break-even point, right? At this point, both companies will have charged a total of what? Okay, we want to know that. All right. So you got to kind of think about this a little bit. You have to figure out what are we going to define the variables as being, right? Whenever we're going to solve a word problem, if it's an application, we have to define what are we going to call x and y. What's x represent? What's y represent? And then maybe how can we tie this information up here into some equations. Now, as you might guess, these are going to be linear equations. Take a second and think about this. Suggestions about the variables. What should maybe the input variable x and what do you think, Zach?
X per mile.
Say it again.
Per mile.
You think the variable is the per mile charge?
Yeah.
So you're saying 0.15?
Yeah.
We got a different answer. Now the per mile charge. Let me ask you something. Let's think about this. The per mile charge. So we've got two different situations. Let's just take the first situation, the Eagle rent-a-car, right? Is the flat fee that a customer changes, or that pays ever gonna change? So that's a constant, right? Okay. Is the amount he's paying per mile going to change for that company? It is? Are you sure? Okay, okay, the total amount he pays is probably gonna change. But the rate he's paying per mile, does that change? Okay, so that's not a variable either. So we gotta think about what's, X is a variable, right? Oh, okay, maybe the number of miles. Okay, the number of miles, all right. So the number of miles driven, now that makes sense as an input variable, doesn't it? Because we want to be able to make a calculation based on how far the person's going to drive, right? Okay, and that's honestly, when you look at word problems like this, typically, this is kind of a strategy. You probably talk about this a ton in middle school. You always want to go to the questions, right? Because typically, the questions are asking about the values of what? The variables or the constants? The variables, right? They're asking for the values of typically the quantities that we're going to assign the variables to. So X is the number of miles driven, X is our input. What is the output of the function that we're building probably supposed to tell us? Cost, okay. All right, so can we come up then with maybe an equation that represents Eagle rent-a-car? Think about what that's saying. So say it again. So Eagle rent-a-car, here's Eagle rent-a-car. Eagle rent-a-car charges a flat fee of $26.04 plus 15 cents per mile. Okay, so our blue equation is going to be for Eagle, so Y equals 0.15. Okay, let's pause there. Does that make sense? Now, so 0.15 looks like a slope then, right? If we're writing this as a linear equation, that's going to be my slope in mx plus b form. What about that reminds us that that's a slope? Yeah, but what about the $0.15 per mile? What about that kind of indicates that might be a slope? Rise over run, maybe the use of the word per, so it's a fraction, right? We're comparing two different quantities, dollars per mile, right? It's just kind of ringing a bell. We haven't done a lot of this so far. But so that kind of keys us in that maybe that's a slope. And then what was the last part you told me? Plus 26.04. Okay, 26.04. Remembering back to doing a lot of the stuff in middle school, what did we call maybe that quantity? What did you call that quantity? Well, it's the y-intercept in terms of the graph, right? Didn't we call that maybe like a fixed cost or start value is probably the terminology you used, right? Is this sort of ringing a bell? Okay, so the output, the total cost is going to be the rate per mile times the number of miles plus the fixed cost, or the flat fee in this case, right? So what about something similar for Easy Rentals? They charge no flat fee, but they charge 77 cents per mile. So what's that equation maybe going to look like? Okay, so we get the rate of 0.77x, and there's no fixed cost to add to it. So then there's our system, isn't it? Right? We've got the equations representing the two rental cars, and when you graphed it, did you get something sort of like? Did you graph it?
Yes.
You get something like that? Okay. So what do you know? We find an ordered pair representing our solution. Now let's interpret that in terms of our answer. So they want to know after how many miles did both companies charge the same amount. So which of those two numbers then must represent the number of miles driven?
X.
X. Okay, so 42. All right, so 42 miles is how far they had to drive. And at that time, what did they both charge? $32.34, right? That's the break-even point. All right. So You'll see a little bit more of this on the next assignment. I haven't quite put it up yet, but I'll put it up today or tomorrow, so it'll be available for the weekend. Going to kind of reintroduce the concept of some applications of this stuff. Let's look at a couple more just mathematical cases though real quick. So try this on Desmos. Solve this linear system.
Whoa.
Okay, what'd you get? Okay, so yeah, a lot of break-even points there, Arthur. So on this one, when we solve this linear system, we find that they're the same line. Now, okay, so in Desmos, how do you know that they're the same line? Okay. Okay, good. So one thing I can do is if I turn this one off, I can see the red line. If I turn this one off, I can see the blue line. But do you actually know that they're the same line? I mean, we can assume that they are here, I guess. But what if I change something very slightly? What if I say this? They still look pretty much the same, don't they? I don't even have to be that severe. I could even probably just do this. Well, there you can kind of start to see that they're different. But you see my point. The graph, Desmos is a powerful tool, but it does, when you leverage technology like this, sometimes there are some limitations, right? That looks at first glance like those are exactly the same line, but if I were to explore this a little more closely, like if I were to just zoom in on a point up here, I can probably start to see that, oh look, they actually do diverge, right? They're not the same line. So there are some limitations to this process. Now to the graphical process. I'm going to show you, and I'm hoping we get to it today. If we don't today, we'll put this off till Monday. Finish this Monday. But there's another method, and we talked about this, I just hinted at this yesterday, this notion of using matrices and linear algebra concepts that revolve around the use of matrices that can just as easily give us solutions, and it's completely unambiguous. You know immediately if there is a single solution, we call it a unique solution, or if the lines are the same line, meaning they're infinite solutions, or if they're parallel, right? They never cross. So you got to be a little bit careful when you're using technology, when you're using graphical technology, but it still is a strong tool. And you know unambiguously that in a situation like this, you know, in most cases it works great. In that case, there's no question. They obviously cross, right? There's the intersection, and if lines intersect, they intersect in one place, right? So that in that case, it works perfect. Very simple to use, and it works great. But there are some situations where, you know, you got to be just a little bit careful. What about something like this right here? And I'm just going to, you know, you could easily graph this yourself, but I'm just going to pull up what the graph looks like. So what do you suppose is going on there if I graph that system? They look parallel, don't they? Right? But once again, you'd have to actually inspect that pretty closely to see that they actually are parallel, right? Now, what are some things we could do? You know, we don't have to just rely on the technology. You know, we know some math too. What are some things we could do to this system to show that, okay, these have to be parallel? I mean, they're find the slope, sure, right? We could go out here and take these and put them into slope-intercept form. Like this one's already in slope-intercept form. What is the slope? It's -1. For this equation right here, the slope is exactly -1. Well, if I put this into slope-intercept form, so let's say I do -8y and I'm going to add the 8x to the other side. I divide both sides by -8. Well, sure enough, I can tell that the slope is exactly -1 there also. And so we can prove it mathematically that they are parallel, right? But the technology, you got to be a little careful. So let's look at a way that we could go back and, when are we out of here? 10 after? Oh, I got all kinds of time. Never mind. So we'll get this. So let's look at another way we can do this. Now go ahead and close up your Chromebooks and get out your graphic calculators. If you don't have one, or don't have it with you, just pair up with somebody. That does. Get close to your name.
The other one didn't have a chart.
All right. Okay, so we mostly use Desmos now. Desmos is in many ways it's easier to use than graphing calculators. But as you go further and further in math, you find that there are some limitations. Desmos, there are some things that it can't do. And so eventually, when you get to college, and we'll probably get even a little exposure to that in here, we'll work with some computer algebra systems, or you'll work with computer algebra systems that have vastly more capacity to solve like symbolic math problems than Desmos does. Desmos is really just a graphing tool with a few bells and whistles, but the calculator is much more than that. One thing the calculator does is it has the capacity to do matrix math. And even though we're not going to explore, hopefully at the end of the year when we're done with everything, that's a topic I'd like to maybe come back to a little bit and just give you a little bit of exposure to that this year. But that sort of depends on if and when we get there. But for now, I want to show you, just consider it kind of a trick. But as you move on in math, you'll come back and you'll understand why this works the way it does. So when you want to use matrices to solve any linear system, and what we're going to find is this even works for big, ugly linear systems that have more than two variables just as easily as it does for small linear systems that are more familiar to us. Here's how you do this. And just kind of follow along with me. You're going to get lots of practice. Today you're just going to dip your toes in the water a little bit. So go to, on your graphing calculator, we're going to go to the matrix screen. And notice it's got its own, it even says matrix. So you go second, matrix. And I made my screen a little bigger so you can see a little better. So we're just going to use matrix A. So what we want to do in the matrix screen, let me explain how this is all structured here. There are three headers. You can choose by name, you can choose each of the matrices that you define to do stuff with, and we will. You can scoot over, and if you go to the math menu, there's a bunch of options that aren't going to make a lot of sense to you, but when you eventually study matrix math, those will all make sense. And then if you scoot over to the edit menu, this is how you build matrices, and that's what we're going to do first. So we're going to build matrix A to represent this linear system. Okay, so we're going to go down, and here's what we want to do. We want to build the matrix. Essentially, we're going to break it up into rows and columns. So think of it this way. Here's our matrix, and each equation represents a row in the matrix. And we're going to define a column for all of the coefficients of x, and a column for all of the coefficients of y, and then an extra column for the constants on the other side. When we write the equations in standard form, as we talked about yesterday, right? ax plus by equals c form, okay? So we're going to need a matrix with two rows and three columns, right? So when we go into, we call that, we have to define the size of the matrix. We always enter the number of rows first and columns second. And I remember that by R.C. Cola. That's way before your time. But R.C. Cola, row before column, so that's how I always keep it straight in my mind. You got to think of probably something different because that won't mean anything to you. That's how I do it. So for matrix A, we just either hit 1 or enter, and now we're defining the size of matrix A. So we're going to do 2 rows, so I hit 2, enter, and then it pops me over to the next slide. 3 for the number of columns, and if I hit enter, it builds the template for me, right? Okay, so we got it? So the way, you can maneuver around the matrices using these arrow keys, but I don't recommend that. Having done a lot of this entry of matrices, it's easier, definitely easier, if you just use the enter button. The way that the enter button is going to work on a matrix, though, it's going to always assume that you're going to enter the elements of the matrix from left to right like you're reading a book, and then it'll page down to the next row, right? So we would enter this by saying -2, enter, then it pops me over to the next slot, -2, enter, -20, enter, and then it jumps me down to the next row. So -4, enter, 2, enter, 0, enter. And there's my matrix, right? I've got it defined. So now, once I've done that, I actually have to quit to get out of the edit mode. So I go second, quit, it goes away. Now I'm gonna go back and do something with that. Here's the part that's gonna be fairly magical. This isn't gonna mean a lot, but it's a great tool. If we go back to the matrix screen and we scoot over to the math menu, we wanna do something with this. We wanna go all the way down to row B, RREF. What that stands for is reduced row echelon form, which is gonna mean nothing to you. I mean, I don't expect it to, but just if you wanna remember what it is, it's reduced row echelon form. It's actually faster, just being pragmatic here, it's actually faster if you're starting on row 1, just to scoot up and go from the bottom, right? So you just scoot up to B, hit enter, and it pulls up that function. So it's reduced row echelon form, and then on the calculator, whenever it opens a set of parentheses like this, and it leaves the cursor there, it means that you need to input something. It's like a function. So we're going to do the reduced row echelon form to what? Well, matrix A. So then we're going to go back to second matrix, and we're going to choose the name of the matrix that we want to use. Well, it's the first one, so I can just either type a 1 or it's already there, so just hit enter. Okay? Everybody there?
Yes.
Okay. What, problems? Let me pause. Oh, okay, so you got it. You got it. Problems? How we doing?
So my sheet is
Oh, that's, you just change it. You just gotta go edit. Then you just put in those numbers. You got it, then -420. Enter, 2, enter. 0, enter. Okay, so it's in there, then you're gonna go. So now you're done with it, you're just gonna second quit. There you go, second matrix. And go to reduce row echelon. Matrix, second matrix. We good? Any other issues?
I could enter.
Yeah. Okay, we good? Okay, back up here, please. So watch what happens. This is pretty cool. Everybody with me? Okay, so if I hit enter, look what it does. It tells me that. Now let's look at. What do you know? I just happened to already have that up here. So let's look at what that's telling us, right? So we started off with. Everybody with me here, please? So here's the matrix that we built. We did this reduced row echelon form function to that matrix, and this is the result. Well, let's interpret this. Now, it gave us back a 2x3 matrix, 2 rows and 3 columns, right? We said that this was equation, let's label these. We said that this was equation 1. This was equation 2. That was the x coefficients, the y coefficients, and the constants, right? So what is that first row telling me then? 1, x plus 0y equals that, right? So isn't that telling me, technically, I mean, what's 0 times y? 0. So 1x plus 0y equals 3.3 repeating is really just saying x equals 3.3 repeating, right? Okay, what's the bottom one telling me then? Y equals 6.6 repeating, right? Okay, make sense? And so if we actually look at the solution of this matrix, rounded to the nearest hundredth, that's it, right? So we would say that this is, in math, we'd say that's a unique solution. We got one solution back. Okay, let's look at what happens with that second example that we tried, right? The second one where the lines overlap. Try this on your calculator. Try that one. So now here's the next question I know you're going to have. Everybody listen, please. I know that the question you're going to have is, well, how do I clear those? You don't. I don't know how to clear them. I've never cleared them in my life. You just go in and right over the top of them. You just reuse the matrix. Or you can pick a new one if you want to, but just reuse A, how about? So you're just going to go back, when you go back to edit that matrix, I'll do it. If you want to follow me, if you think you got it, that's fine, but if you want to follow me, I'll talk you through it. So I would quit. Oops, I'll clear it. I'm going to go second, matrix, edit. Matrix 1. And then all I got to do is just go back and change the numbers, right? So instead of a -2, I've got a 15. Instead of a -2 for y, I've got a 15, etc. Right? Just keep going. Oops. Well, I got these. Somehow I got these kind of stuff.
X plus y equals 3.3.
Oh, there we go. That's right. Okay, here we go. Back up here. So you may not have finished, but hopefully most people did. This is what, if you didn't get a chance to finish though, this is what you would do, right?
Yes.
We're just going to go back. I called mine matrix B, but you could just make it matrix A again. Just go in and enter the coefficients and the constants. And when you hit reduced row echelon form, you got something weird. I told you that. Okay. Now let's interpret this, because this doesn't look like the solution we got last time. Think what that's math gods are telling us in that first row right there. What's that saying? That's the coefficient of x, right? So we get 1x plus 1y equals 3.38. Right?
3.8, not 3.8.
Oh, whoops, 3.8. Okay? That's the solution it gives me. What does this second row say? 0 plus 0 equals 0. Okay, so let's combine those, and they tell us something significant. If we look at the graph of this, and we actually graphed this one, right? This was, yeah, there was one line, and wasn't that it, right? It was this one, right? Only that was at 5. Okay, if I look at this line, what did we say the slope of that line was? We calculated it, didn't we? Oh, I guess we didn't. But what is the slope? If I take this equation and I solve for y, 5y equals negative 5x plus 19. If I divide both sides by 5, don't I get negative x plus 19 over 5, some number, right? So the slope is negative 1, right? Let's look at our graph. What's the y-intercept? So what's the equation of that line? I get y equals negative x plus 3.8. So didn't this give us, it actually gave us, in standard form, it gave us the equation of that line, didn't it? If we wanted it, it's there. More importantly, the second row told us that 0 equals 0, which is always true, right? So whenever you get an answer back that doesn't look like this, right, that doesn't look like x equals a number and y equals a number, you know that it's not a unique solution. You're not getting a single point. If the bottom row is all zeros, guaranteed, that means that it's the same line. There are an infinite number of solutions because this is always true. That's an easy way to sort of remember that. So we call this in math, if you get that case, where the bottom row is 0 equals 0, it's infinitely many solutions, and that is a case of a consistent system, right? They're the same line. Okay. All right, what about the other case? If we were to do this one, right? Now, this is one where, in order to enter this into a matrix, what would I have to do to that bottom equation? Oh, so it has to be in standard form, right? I've got to have it as ax plus by equals c, so I'd have to add that x over to this side. X plus y equals 10. And if I do that, everybody agree that's what it's going to look like? I'm going to get negative 8, 0 for my first row, 1, 1, 10 for my second row. Okay, this is the one where the lines were parallel, right? The third example that we graphed. And we said there were no solutions, right? Because they never crossed. But we weren't sure. We couldn't tell if they were exactly parallel. Well, how do we interpret this result that we get when we use the matrix method? So the first line tells us x plus y equals 0. Okay, well that's fine. But what does this second row tell us? Red flags go up. Yeah, it tells us 0x plus 0y, which is 0, equals 1. Is that true ever? So what do you think the math gods are telling us when we get the bottom row of the matrix that we get back says 0 equals 1? No solutions, right? That can never happen. And so this is no solutions. It's an inconsistent system, right? The lines never cross. Okay? Make sense? All right. Are we out of here at 25? Okay. So last example then. This will work out just about fine. So what about a system like this thing, right? We kind of hinted at these yesterday, where we've got x's and y's and z's, and we looked at what a graph might look like. We've got the x-axis and the y-axis, and we add another axis coming out of the board, perpendicular to the board, the z-axis. And so this represents physically not just a plane, it represents a volume, right? So each one of these is an equation of something that exists in the volume, not just on the plane, right? And so one way to visualize this, I think I made a, oh, hang on, I've got a picture here somewhere. Right there. Okay, one way to kind of think about this is interaction of planes. Instead of looking at two lines and where they intersect, when we graph three equations that have x's and y's and z's. Each one of those represents a plane, and we'll talk more about this later. But there are different ways that the planes can exist in the same space. They could all be parallel to each other and never cross. That's going to be no solution, right? They could not be parallel, but still never all three of them cross at the same place. So that's still no solution. There's another example of the way that the three planes might never intersect. Really, the only way that they could all intersect is something similar to this. They don't have to be at right angles, but if all three of the planes join in a single location, then that's the solution. It's still a point, right? But now the point is represented by coordinates in the x direction, the y direction, and the z direction, right? So like in the room, can you think of a place where you could point to a point that is clearly the intersection of three planes? I was pointing at the corner. Okay, the corner would work, right? Like if I take this corner up here, I've got the front of the room represents a plane, ceiling represents a plane, and the far wall represents a plane, and they all meet at that common point, right? Whereas if we looked at maybe the three planes, the ceiling of this floor, the floor of this floor, and we went down to second hall, right? And looked at the floor there, if we looked at all three of those planes, they're parallel and they never cross. Okay, so if they all happen to cross in a situation like this, perhaps there could be infinitely many solutions also, right? They all cross along a common line. If we want to solve this system, clearly we can't graph this on Desmos, can we? Right? Desmos, we're limited to the XY plane on Desmos, so that's not even an option. But the method I just showed you still works. Still works just as well. Only difference being now, instead of a 2x3 system, 2 rows and 3 columns, how are we going to define our matrix? 3x4, 3 rows and 4 columns. So it just looks like that, right? Okay, but if I do the trick, I still get back the same kind of result. So in this case right here, if I were going to solve this system representing that linear system, how would I, based on what we just talked about, how would I interpret this result? Right? I'm not getting a situation where I get like x equals a number, y equals a number, z equals a number.
1x plus 2z equals 2.
What is that bottom row telling me? No solution. It's telling me 0 equals 1. Right? So it's not a case where they all intersect in a single point. Now, we can go further into this, and we're running out of time today, but if I look at these top 2 rows, they'll actually tell me more information about what kind of no solution is it. But that's probably more than we have time for today.
So you were
Okay.
recording?
What's that? I did record, yes.